Hello, and welcome to video lesson 18 on principal and maximum shear stresses. Our learning objectives for this lesson are for you to be able to draw the rotation of a stress element into its principal orientation. You should be able to define principal stress, principal angle, and maximum in-plane shear stress. And you should be able to calculate principal stresses and principal angles for a plane stress element in any orientation. So for this section, you should read Beer and Johnston, section 7.1. So let's start with talking about what we're doing with stress transformation in general and what it means for an element to be in a principal orientation. So remember back in lesson 16, when we talked about combined stresses, we had chosen a natural X, Y, Z coordinate system, and we drew stress elements on the X, Y, and Z faces. And we had combined loading effects. And we had, for instance, shear and normal force on several of the faces of the element, and it would end up looking somewhat like this. However, it's usually not enough to know whether material yields to just have stress results like this, like what we had in lesson 16. We usually need to understand a little bit more about the state of stress at a particular point. In particular, what we want to obtain from stress analysis is usually the principal stresses. And by principal stresses, we mean the stresses on a material, on this element of material that I would get by rotating this element into an orientation where the shear stresses would go away. So what's important to know about shear stress is that, what's important to know about principal stresses is that shear stress vanishes. In other words, tau is equal to 0 on the rotated element faces when the element is rotated into principal orientation. As you remember from lesson 17, our last lesson, stresses change as we rotate the plane. And we saw that it could follow a circular trajectory. But we knew that the components of whatever force, whatever traction was acting on a particular plane would have to be resolved into normal and shear components, and we would also have a change in area that had to be accounted for. So the stresses on an oblique plane were dependent on the angle of rotation of the oblique plane with respect to the cross section. And something similar is happening here. So as I change the orientation of the X face and the Y face through a rotation, I'll end up with different stresses. However, there's always going to be an orientation where the shear stresses go away. And when the shear stresses go away, the stresses that are on the element face are the principal stresses. Now, the principal angle, the way I've drawn it here, is going to rotate the element such that the most positive principal stress, P1, is on the X face, and the least positive, or the smaller, in magnitude, stress, sigma P2, would be on the Y face, the way this is transformed. So it's important to note that P1 and P2 are principal stresses. However, in all solid mechanics problems, there are always 3 principal stresses. But for plane stress problems, 0 is going to be the 3rd principal stress. And always, if we see them ordered in terms of sigma 1, sigma 2, sigma 3, Sigma 1 is the most tensile, it's the most positive stress. Sigma 2 is the middle stress. Sigma 3 is the least positive or the most compressive principal stress. So how do we figure out, so we need to know these things, what these are numerically, because these principal stresses are going to feed failure criterion. And we're going to talk about failure criteria in an upcoming session. So we need to know how to calculate the principal stresses. And if I have a stress element, I can calculate sigma P1 and sigma P2, the two principal stresses that are on the element, relatively easily. The formula here says sigma P1 and sigma P2 equals sigma x plus sigma y over 2. That's called the average stress. And then I would have one, whereas P1 would be positive and P2 it would be negative. And then I would have the square root of the entire quantity under the radical being sigma x minus sigma y over 2 quantity squared plus tau xy squared. So I would just figure out what those numbers were from the plane stress element, put them right in there, and I've got the principal stresses. If I want to know how far I have to rotate my element, I would know that tangent of 2 times the principal angle to get it to a principal orientation, maybe not this principal orientation, but a principal orientation would be present if I had tangent of 2 theta p equal to 2 tau xy over sigma x minus sigma y. And the maximum in plane shear stress is going to be equal to sigma P1 minus sigma P2 over 2. And then there is an angle, we call it theta S, that tells me the inclination of the plane where I have maximum shear stress. Now, in a lot of materials, this is a very significant plane because most tensile failure actually happens because of dislocations sliding through materials, and it takes shear stresses to make that happen. So when shear stresses reach a critical level, you'll usually have failure along this kind of a band, and you'll usually see that. So we want to know the orientation often of where we would have the maximum shear, and if I wanted to do that, I would be aware that the shear angle is equal to the principal angle plus or minus 45 degrees. So I could figure that out also from the equation that says tangent of 2 theta s equals negative sigma x minus sigma y over 2 tau xy. So if I want to calculate these things, it's very straightforward. I just use these equations. You don't necessarily need to know how they're derived, just know that they are derived by considering equilibrium on small pieces of the stress element. But you don't really need to know how those are derived for this course. All right, so let's consider an example of the theory that we just learned. So let's calculate sigma P1 and sigma P2, the two principal stresses, tau max, the maximum in plane shear stress, theta p, the principal angle, and theta s, for the stress element that we see here. So on this stress element, sigma x is equal to negative 24 ksi. It's pushing in, it's compressive. We have the arrows drawn such that they are pointing both towards the bottom right hand and the top left hand corner. And when that happens, that is negative stress on our element with our sign convention for plane stress. And we have no stress in the y direction, so sigma y is equal to 0. So if I wanted to apply the formulas, I can do that fairly easily. It's pretty straightforward to do that. Sigma P1 is going to be equal to negative 24 plus 0 divided by 2 plus the square root of negative 24 minus 0 over 2 quantity squared plus negative 6 squared. And when I do the simplification there, I get sigma P1 of 1.4 KSI. Sigma P2 would be given by taking the negative sign in this relationship. And we would have negative 12 minus the square root of 144 plus 36, which is this thing here. And I would have negative 25.4 KSI. Tau max in plane is given to me as 1.4 minus negative 25.4 over 2, or 13.4 KSI, using the equation that says tau max in plane is equal to sigma P1 minus sigma P2 over 2. So the difference in the principal stresses divided by 2 gives me the magnitude of the maximum in plane shear stress. Now for theta P, that would be given to me as tangent inverse of 2 times negative 6 over negative 24 minus 0, negative 6 being the shear stress tau xy, negative 24 being sigma x, 0 being sigma y. Divide that by 2, and then add or subtract 90 degrees, and we'll talk about why in the next section, in the next video lesson. But just keep in mind that the arc tangent function is only valid for quadrants 1 and 4. So we don't have every angle available to us for rotation with this equation here. So we have to do an inverse tangent to solve for theta P. And when we do that, solve for theta P, we end up with theta P equals tangent inverse of this quantity divided by 2, and then we would add plus or minus 90. All the 90 degrees does is it just flips the x and y subscripts, or the x prime and y prime subscripts, whenever we're doing a rotation of an element. And we'll see that later on. And the shear planes, the max shear planes, would happen at an orientation of theta P plus or minus 45 degrees. And then that would also be plus or minus 90 degrees. Because I have another shear plane that would be like this, that would also be a maximal shear plane as well. I didn't draw that on this element, but we'll see why that's the case when we take a look at Moore's circle in the next session. So we would have max shear at 58.28 plus or minus 90 degrees. So a max shear failure would come in about like that on the element. So a max shear failure about through there. And we will examine this example a little bit more in the next video. But I did want to talk briefly about the general problem. It's important to understand Moore's circle, especially for civils, because you will apply it quite frequently in numerous places, especially geotechnical engineering, when you take a look at the shear strength of soils and you do direct shear tests in geotech. So it's important to understand Moore's circle. It gives you a visual way of thinking about these things, and it's important to know what the principal stresses are. However, for computational purposes, much of this is going to be done for you in a package like SolidWorks or anything that you would want to work with that would be finite element related. So if we're talking about 3D problems, most of your analysis is probably going to be computerized. But I did want you to understand that if we write out the stress tensor components in matrix form, the first row is sigma xx, tau xy, tau xz, the second row being tau yx, sigma yy, and tau yz, and the third row being tau Zx, tau Zy, sigma Zz, we would just find the principal stresses as the eigenvalues of this matrix, and we have many good programming, computer programming packages that, like MATLAB, that can do that for us in the blink of an eye. And if we want the principal directions, the orientation of these faces where we have the shear stresses vanish, we would get those relative to the original coordinates by just taking the eigenvectors of this matrix. So it's a linear algebra problem of great importance to solid mechanics, but it's pretty easy to get the principal stresses. So at the end of the day, the thing that you really need to remember from this lesson is that principal stresses are the stresses where the shear stresses go away. And we have ways to calculate those for any state of stress in plane stress. And if it's a 3D problem, we would just be doing eigenanalysis. That's it for video lesson 18.